Okay, I think now it's being recorded. Okay, so you can still see my lecture note, right? Okay, great. Okay, so we start proof. So look at the convergence theorem. So what is the assumption? Assumption is there's a characteristic function that converges. That's one assumption. And there's another assumption, which is this limiting function is continuous at the origin. So characteristic function is, we proved that by it's continuous. Characteristic function is continuous. But the limit may not be continuous, but we claim that the limit is also characteristic function, so it will be continuous everywhere. But we don't need that much assumption. We just need the continuous at the origin. Then the corresponding distribution function converges. That's the statement. So first, we will prove this corresponding distribution function is tight. And that's coming from this continuity at the origin. So we proved that last time. So we proved that the corresponding distribution function is tight. That's what we did from this one-page calculation, starting from the continuity here, the continuity of characteristic function at the origin. And then this inequality becomes tightness of the distribution function. So why do we need this thing? Because we already proved something nice about the tightness. We already proved. We proved a lemma that says if this sequence of distribution function is tight, if Fn, so these are distribution function, is tight, then the limit point exists, then the limit point exists. So we prove this by showing that first we show that every rational point there's a limit exists and extending to every place. So limit point exists and or limit function exists. Okay, let me change that to limit function. Limit function exists, and it is a distribution function also. So limit function is not only exists, but it also satisfies non-decreasing, right continuous, and going to 0 and 1 on both infinity. So we had this lemma. Where was this lemma? That lemma, if you don't remember, that was somewhere before. Yeah, here. This is the lemma. We actually prove the other way also. If there's a convergence of distribution to another distribution function, then the sequence must be tight. But the second thing is what we need. If the sequence is tight, then the limit exists. It's not so limit exists. We also show that the limit exists. And the limit is the distribution function. So we showed this, and we will use this lemma. And therefore, we just show that the distribution function is tight. And therefore, yeah, right, because here we should just show that the distribution function is tight, right? Therefore, Fn has a limit point, has a limit function. Limit distribution function, because we know that the limit is also distribution function by this above lemma. Okay, so that's why we make a fuss about this distribution lemma about this distribution function. Okay, so now we use that lemma. We don't need it anymore. So let's call this function. So what do we need? Well, we have a limit distribution function, And that limit distribution function, so Fn converges to this limit distribution function, but it's one of the limit. So we have to show that this limit is unique limit. So it has a limit distribution function, meaning there exists a subsequence f and k that converges to f, which is the limit distribution function. So far it's just this. So far is this thing. So there's a subsequence that converges to certain limit. Okay, then this means that for each distribution function, of course, there will be characteristic function. Let's call it f and k. And f and k was what was the definition? Characteristic function is the integral of e to the I theta x d f and k x. That was the definition of the characteristic function. And this will converge. So if f and k converges, so converges means that f and k converges to f in a weakly convergent, meaning that it's if you integrate with any bounded function, that was the original definition of the convergence. So here so that's convergence in distribution to recall. And convergence of distribution is if you integrate with respect to some bounded function, then those integral converges. And here we have bounded function because that's always modulus 1. So of course this will converge to this one by definition of the convergence of the distribution, and which is exactly the characteristic function for f. Okay, so let's write down phi of f. This is the characteristic function for but what was the assumption? Assumption was assumption of the theorem, assumption of our theorem is our phi n, the whole sequence converges to phi, right? Assumption was that our whole sequence converges to phi, which means any subsequence will also converges to phi, and therefore phi f, our phi f, which is coming from the limit distribution function, the limit distribution function is also equal to phi. So that's so we claim that the full sequence converges to this f, which whose characteristic function is phi. So this is the claim. If not, there must be some subsequence, another subsequence. If not, there is another subsequence. There are another subsequence f and k, which converges to some other f tilde, for example. And then using the above logic, you will get phi of f tilde, which will also be phi. And that means phi of f will be equal to phi of f tilde. So if there's another subsequence which has the different limit points that will have the same limiting characteristic function, and this means f is equal to f tilde by what's the, so if distribution function is same, then of course the characteristic function is same. The other way around is also true because we proved last time the thing that I may mess up with the sign. So that's exactly the inversion formula. So if the characteristic functions are same, since we can find the distribution function from the characteristic function using inversion formula, so if there's another distribution function as a limit, then they must be same as the previous distribution function. So there must be unique limit point. So the whole sequence must have a single, so we just show that there must be single limit point, single limit function. Okay, so that's the end of all the necessary. So what we will need is this final theorem, Levy's convergence theorem. If the characteristic function converges, then distribution function converges. So we just have to calculate the characteristic function for the central limit theorem. So let's now calculate to prove the central limit theorem. Okay, what? Central limit theorem. Okay, so let's remind what's the statement of the central limit theorem. We have sequence of random variable and 1 to infinity, sequence of random variable. And they are IID random variable, which means independent, they are all independent, and distribution same, identically distributed. And one more condition that they must have second moment finite, so that we can talk about the variance. And then we define partial sum. So using S from the sum, so N is how many terms we added. Okay. And then we define okay, so mu is the mean value. And it exists because our assumption that the second moment is finite. And also we define the variance to be this. The sigma squared is the variance. Okay, and that also exists because of the second moment finite condition. And then we will normalize this Sn by square root of n times the variance, sigma, standard deviation. Okay, so this is the random variable. This is a sequence of random variable, right? For each n. And that converges in distribution in distribution to the standard normal distribution. So that's the statement of the central limit theorem. Okay, so what we need is to prove that the corresponding we need to prove because of this Levy's convergence theorem, using Levy's convergence theorem, that the corresponding characteristic function converges. So what we need is phi of this characteristic function. Oh, I'm sorry. Here I didn't subtract the mean. So yeah, let's. So we have to subtract the mean just a second. So we have to subtract the mean. But maybe later we will just put the mean to 0, just to be easy to write down. So, okay, so let's keep the mean. So this is minus n mu. So we just have to show that this function, this is a function in theta, this function converges to characteristic function of the standard normal random variable. What was that? We calculated that. That was e to the I theta x, and then we have to write down the standard normal density function. So we calculate this integral. Then what did we obtain? We obtain e to the minus, it's the same form as the standard normal density function. So that's what we need to show. We just need to show this fact. Okay. Okay, so let's show that. So first, phi of Sn minus n mu divided by sigma square root of n. This can be written as phi of, so I will rewrite as a sum, x1 minus mu sigma square root of n plus x2 minus mu sigma square root of n plus, and so on, up to xn minus mu sigma n. I rewrote as a sum. Why did I rewrote it? Because the characteristic function had a property, if it is a sum of the independent random variable, then the characteristic function becomes a product of each independent random variable. We proved that when we first defined the characteristic function, that was very simple to prove. So this becomes the characteristic, for the first characteristic function of the first one, yeah, we can actually, yeah, I can, yeah, okay, yes. And characteristic function of the second one, and so product all the way to characteristic function of the last one. So here is using independence. Using independence of these random variables. And since they are all IID, they are all same characteristic function. They are all same. So these are just nth power of the first characteristic function. So I will write down without the index x1, just x minus mu, because they have all same characteristic function. So this is just this to the power n. So we just need to calculate the characteristic function of single random variable. Okay. So let me try to calculate the characteristic function of simpler case, just without x minus mu or sigma n. Okay, so, and that was by definition expectation of e to the I theta x. That's the definition. And let's expand Taylor series expansion in theta. Then we have 1 plus I theta plus 1/2 theta squared, but with the minus sign because there's an I, plus higher orders, and I will write down the higher orders in the following form. So big O with the higher order of order large degree greater or equal to 3. So this big O notation is this quantity is at most behave like some constant times theta to the power 3. Okay. And then we can take the expectation, of course, at each term, because expectation is a linear operator, like integral. So we have 1, expectation of 1 is 1, identity expectation of sigma, expectation. Oh, and I forgot, I'm sorry, x, I forgot x. Oh, what am I doing? I forgot all the x's, right? X squared. Yeah, then the other part also contains x's, power 3 and so on. Okay. Okay, so first one is e to the I theta times expectation of x. The second term is minus 1/2 theta squared, expectation of x squared. And there will be other terms that I'm ignoring for the moment. And then I'm gonna somehow show that the other part can be ignored. So let's first consider, let's remind this fact. So log of 1 plus x, if you Taylor expand this quantity, log of 1 plus x, yeah, let me just write down. So I'm just writing up to the degree 2. This is some exercise in calculus. So that, and from here, we will calculate the log of above 5x theta. So I just take log on the, I just take the log on this part, log on that part. Then what do we have? What do we have? So if you look at this underlined part, it's 1 plus something. And this something corresponds to this x. So I have to write this, the whole thing. And then the next term is minus 1/2 times the something squared. So let's write also that. Minus 1/2 times something squared. And so we have to square this part. And the leading term, the lowest order in theta term is coming from the square of the first term. What is that? That's minus theta squared, because I squared is minus 1, then expectation of x squared. So I only keep up to degree 2. Okay, then what do we get? We get this, and then minus 1/2 theta squared, and then we have two terms, expectation of x squared minus expectation of x squared. Good. So this gives this term. This gives this term. Here we have then other terms. And what is this? This is the variance. Variance of x. Okay, and we will show that we have to take care of the other part that we are ignoring. So yeah, the goal is to show that we can ignore the other parts. Okay. Okay, so let's define notation for the other parts. So Rn of x define. So Rn of x is by definition, so we start from expansion of this exponential function. And if you expand this exponential function, then, okay, so we have 1 plus ix minus x squared over 2. So in general, all the way up to, if I expand up to nth term, then we will have ix to the power n divided by n factorial. So that's the nth term. So if I subtract this nth term, then we will define the as a remainder. So define the remainders as following. So above, we only subtract, we consider R2, right? Because we kept up to degree 2. Okay, for example, R0 is e to the ix minus 1. That's 0. We subtract only the 0 degree term. And we want to have a bound of this term. So this term can be written as integral of, so I e to the I t dt. So how did I obtain this one? Just I took the derivative of this part. I took the derivative of this one and integrate from 0 to x. Does it make sense? Because if you take the antiderivative, then you will get e to the ix, and evaluate at x and 0, then you get exactly this one. Okay, so now we want to find what is the size of that one. So this is the size. And if you put the absolute value inside the integrand, of course, that will increase. And absolute value of e to the it is, we learned that it's also all complex number on the unit circle, so that's 1. So this gives x. This gives exactly, it's an integration of 1 from 0 to x. So it's, so that's the x. Why did I write it that way? That's x. Okay, so this thing is x. Yeah, when x is positive, it's this inequality is only when x is positive, because if x is negative, then so it should be absolute value of x. Okay, let me write absolute value over here. So it's absolute value of x. Okay. Then I say this is minimum. It's against the absolute value of x is smaller than absolute value of x, and we will just consider that it's x is smaller than 2. So we will only consider x to be smaller than 2. So we assuming that's silly, but so we consider only in the neighborhood of the zeros. Okay, so that's the bound of R0. Oh, no, that's stupid. I'm sorry. So I'm not assuming anything. So where is this thing coming from? Okay, where is this coming from? Okay, that was really stupid. 2 is coming from very obvious fact that from here directly. It's a subtraction of the 2 terms, and both of them is maximum 1. It has a modulus 1. So this part is of course smaller than taking the absolute value on each term. And that's 2. So this expression R0 is less than absolute value of x from this one inequality, but from just from this original expression, it's obviously smaller than 2. So it must be smaller than both absolute value of x and 2 for all x. Okay, so I just saved myself from making a stupid remark. Okay, then I will generalize this fact to arbitrary n. So we have Rn. This is all bounded. So we just have found the bound of the remainder for R0. Now for general R, we have the following bound. For any x, this remainder is given by this. Okay, so you can check that if n equals 0, then the first term will give 2, and the second term will give absolute value of x. So it gives the correct, includes the previous case. And the proof of this lemma is exactly the same calculation as I did for R0, but just by induction. Let's quickly show. So if I take the derivative of Rn, then what do you get? We get, so let's look at this expression here. You get I times e to the ix from the first term, right? And if you look at this part, so derivative will remove 1. Derivative of this term will give I, right? So in fact, all the term will have I multiplied, but the form of the rest of the form will be same as before. And but derivative of the degree n will give the degree 1 less. So the final term will end not at an n degree, but n minus 1's degree. So what we have is I times r n minus 1. So the remainder has this relation. And therefore, again, using the same, so I can rewrite this Rn of x as Rn prime of t dt integrate from 0 to 1. Same strategy. And then I use that Rn prime can be written as Rn minus 1 times I then we want to find the size of that. So I take the absolute value. And then again, absolute value is, oh no, it's not from 0 to 1, it's from 0 to x, sorry. 0 to x, 0 to x, and 0 to x modulus. And here it's a modulus of Rn t dt. And induction means I can use the lemma here. I can use the lemma here. So that's the how we use induction. We assume this lemma is true all the way up to n minus 1, and then we want to prove the fact at n. So I use the exact statement of the lemma over here. It's minimum of e t to the power n minus 1 over n minus 1 factorial, and t to the t modulus to the power n over n factorial and dt. Okay, and so we just have to calculate the integral of each term. So that's just t to the power something, so it's easy to integrate. The first term, you get t to the power 1 more power and factorial. And the second term also 1 more antiderivative, then 1 more power and plus 1 factorial. But now we have to integrate from 0 to x. So the t will change into x. So that's the end of proof. That's the end of proof. So we found some bound, some estimate of this remainder term, and we can use it for R2. Yeah, let me copy this lemma because I cannot remember. Okay. So we have this lemma, and we had phi of x theta, and we will subtract the first two terms. Minus theta squared over 2, expectation of x squared, right? And the rest, so just keep the first two terms. And So what is this? This is, okay, so this thing was by definition, it's the expectation of what? E to the I theta x, right? That's the definition. So the whole thing is expectation of e to the I theta x from the first one. And the other part can be written as 1 plus I theta x minus theta squared over 2x squared. So this is exactly R2 of I theta x. The remainder term, just removing the first two terms from the exponential function. Oh, I'm sorry. Let me. Oh, I skipped one page. Okay. Where is the definition of Rn? Let me recall the definition of Rn here. Copy. Paste. So here is the definition of Rn. Oh, yeah, I think I made a mistake. So here, no I. Right? So if I look at the definition of Rn, it's subtracting the first Taylor expansion of this part. And if I compare with this term, the small x part is theta times capital X. So I just have to replace the small x by theta times capital X. Okay, so this is expectation of capital R2 theta x, and we have so we want to find the size of this thing. So capital. So we want to find the absolute value of this quantity. And again, absolute value of the expectation is expectation of the absolute value, like absolute value of the integral is integral of this absolute value. So we can take the absolute value first. And we found the size of that one from this lemma. So using the lemma, over here, it's the minimum expectation of what? I just have to put theta x into this small x, 2 theta squared x squared over 2. 2 factorial is 2. And power 3. So this is theta times x to the power 3 divided by 3 factorial, which is 6. Yeah, to be more, yeah, so let's put the minimum inside for now. Okay, so we can put the theta squared. Here we have theta squared. Here we have theta to the power 3. So maybe we can put the theta squared out and can write as minimum between x squared. 2 is canceled. 2 canceled from both sides. And the other part has a theta to the power 3, but one theta, 2 of them was moved out. So we have only one theta times x to the power 3 divided by 6. So that gives the bound. And let's consider as theta going to 0. As if theta is small enough, then okay, theta is small enough. What happens to this random variable? This random variable will go to, so this will converge to x squared as theta going to 0. Because for any x, for any capital X, the second term will be going to 0. Second term will be 0 for any capital X. So eventually x squared will be bigger than the second term, theta times x to the cube over 6. So eventually it will go to x squared as theta going to 0. Right? Okay, so that means as theta going to 0, this will converge to the e to the x squared. So this part is a random variable that converges to x squared. This part is the random variable that converges to the x squared. And it's also bounded by x squared. It's bounded by x squared. And so so here we are again using some theorem about the convergence of the integral. So the expectation of the function that converges to some other function is same, and it converges to the expectation of the limiting function, which is so the function converges to x squared, so the expectation of also converges to the expectation of the limit function. And here this is true because it's not bounded convergence theorem. It's what is it? Forgot the name. Does anyone know? So here, this function is bounded by x squared, another function, and this another function is integrable. This another function is integrable because we assume that the second moment is finite, which means there's another bound of this whole function, which is integrable. In such case, expectation of the function converges to the expectation of the limit function. I forgot the name of this theorem. Is this? Yeah, nominated convergence. So similar to the bounded convergence, but bounded convergence theorem is has a bound by a single number. So bounded by a constant function. But here its dominated convergence is bounded by some function which is integrable. Okay, let me repeat. So here we have some function that converges to another function x squared as theta going to 0. And all this function is bounded by x squared. It's dominated by x squared, in other words, and dominated for all values of theta. And this dominating function x squared is also integrable. And in such case, the limit of expectation is given by expectation of the limit, like the case of the bounded convergence theorem. Okay. Okay, so we showed this part is bounded by this one, especially for some neighborhood of theta near 0. And okay, and for example, so as a result, not for example, as a result, this thing going to 0 as theta going to 0. That follows from the above. Yeah, here we have this thing. Theta going to 0, then of course theta squared times something finite goes to 0. Okay, so now we can estimate. So let's go back to our, yes, so here, this is what we want to compute. That's the characteristic function of that converges to characteristic function of the standard normal random variable. This is supposed to converge to e to the minus theta squared over 2. So let's calculate this one. So let me remind. So we will apply what we have to this one, theta of phi of x minus mu over sigma square root of n theta. Okay, so this thing is equal to 1 plus theta expectation of x minus mu theta I. Yeah, let me put one more step just to remind you what was the definition. Definition was expectation of I theta times whatever random variable that we are interested. So that's this first term. The second term is minus theta squared over 2 sigma squared and expectation of x minus mu squared. Right, yes. And the higher terms. Yeah, we can compute. So what is this one? That's obviously 0. Because mu is expectation of x. Mu is expectation of x. And what is this part? That's expectation of x minus mu to the power 2. That's definition of the variance. That's the definition of variance. So this is exactly sigma squared. So that cancels with this sigma squared. So at the end, we get 1 minus sigma square over 2n. That's it. And the higher order terms. Good. Okay. But what we want was Sn minus n mu, right? That's what we want. And that was given by above to the power n, right? And that's exactly 1 minus theta squared 2n and something else to the power n, right? Yeah, and then here is what we need here. Oh, no. Yeah, another mistake. Yeah, I really, guys, I'm sorry. So here. Okay, well, let me correct here. This is a very stupid mistake. So this minimum of x squared and theta times whatever, x to the power 3, I said this thing converges to x squared as theta going to 0. Is it? That's not true. Can you see that this is not? So it's minimum of some number. Yeah.
But Prof, you were explaining it, so I thought it was correct, because if theta is equal to 0, then the minimum will not be x squared.
Right. Yeah, you're right. Yeah, thank you.
Yeah, but you were still explaining, so I thought it was.
No, you should already know that I'm very, very dumb. It's a lot of mistake. So here it's so yeah, I don't know what happens to my brain when I explain. But of course, the minimum of something and something close to 0 will be 0. So it goes to 0 as theta going to 0. Because this, for any value of capital X, eventually the second term, theta times x to the power 3 will go to 0, right? For any value of x. The other comments are correct. They are bounded by x squared, and the x squared is the dominating integrable function. Therefore, using the dominating convergence theorem, you will have 0 here, which means that's 0. This is 0. So as theta going to 0, this thing goes to 0. Especially, so this is theta squared times something that goes to 0. Okay. Okay, so we can, I will write this one more accurately. So this can be written as following. It's theta squared times something that goes to 0. So I'm writing in this way, even though theta squared itself is going to 0, because it's even faster going to 0 than theta squared. That's the thing that I want to emphasize. So it's theta squared times something that goes to 0, and that's the notation for that. This, I use small o, that's important. This is something that goes to 0, as theta goes to 0. That's the meaning. Okay, so we have this estimate. And what is this R2? R2 is exactly what's coming. Exactly what's coming here. That's exactly expectation of R2 theta of, now we have this complicated case. Because we kept up to first two terms, the rest is the remainder, right? Okay, so what we found is that this part is bounded by theta squared times something that goes to zero faster, something that goes to zero as theta going to zero. I think I made another mistake. Let's see. Yeah. So if actually, so yeah, actually, if I look at this part, you can see that it's r squared, r2 of theta over square root of n sigma times x minus mu. So it was R2 was bounded by theta squared if it's written in this form, theta times x. Now if I look at here, then the theta is replaced by theta over sigma over square root of n. So in this place, in the place of theta, we should put this, the whole thing. So this theta squared and small of theta over square root of sigma, like that. Okay, so let's rewrite it. So this is identity 1 minus 2n plus something that goes like this times something that goes small as theta over square root of n. So I didn't write the sigma because all this part is ambiguous anyway. This part is ambiguous anyway, so we can skip writing of the sigma. Okay. Okay, so now we have to take the power n, and there we will use this. How did we define e to the x when we first learned in calculus? E to the x is 1 plus x over n to the power n, limit n going to infinity. That's how we learn to define the exponential function when we first learn in calculus. So let's use that. So this converges to as, so this is similar expression, right? It's like this expression, except that what is the x part? So if as n growing, as the part that relates to x is, okay, let me rewrite once more. Let me put one more step. So I can rewrite this one as 1 minus 1 plus 1 over n times this plus this over times O of this one. I just rewrote it, the same expression. There are too many brackets, so let's use the square bracket also. Okay, so I just rewrote this one to compare with this one. Okay, and therefore this expression, this part becomes small x in here. So that will converge to e to the this one as this will converge to this one as n grows to infinity. Good. So, good, right? And this thing is something that goes to 0 if the argument goes to 0, right? And if n going to infinity for any theta, argument goes to 0, right? This part will go to 0. So actually this thing is going to 0 as n going to infinity. So we just found that as n going to infinity, that's the limit of this one. Wow. Finally, in 7 lectures, we've proved the central limit theorem. Proof of central limit theorem done. So we proved that characteristic function converges to this boxed part. And that's the proof, because Levy's convergence theorem says it's enough to prove the characteristic converge, because then the distribution function converges. And central limit theorem is a statement about the convergence in distribution. Okay, so now the quiz will be, you can say that we proved the central limit theorem. Yeah, let me just check whether I put the quiz in that way. Okay. So edit question. Did we finish the proof of the central limit theorem? Ah, okay. So save and publish. Yeah, I think I just published, but what it's made available. Yeah, it will be made available a little later, after 5 minutes.
I mean, I can see it now.
Oh, you can see now. Okay. I want to see whether it can be made available right away. Oh yeah, here is this. I can change the time. Where's the save button? Ah, save button. You must have a student section. Save. Okay, so it should be available now. Okay, so we can do something else from next time. Any question? Okay, then you can, I believe anybody did go to a quiz and successfully submit the answer?
Yeah, I submitted the answer.
Okay, good. Okay. So then let's see. Next time I will start this martingale theory, but we have to start from conditional expectation. So we already learned conditional probability, what that is, but we have to extend this a little bit. to conditional expectation, and martingale theory is based on those concepts. Okay, so see you next time.
Yeah, Prof, you upload the video?
Oh yeah, I'm going to upload video faster.
Okay.
Yeah, sorry for.
Yes,
But I think the previous videos are all uploaded, right?
yes,
Yeah,
Prof.
yeah. I will upload the videos and lectures by today. I should be stop procrastinating. Okay. Okay, so let me stop recording. It's not good to say that, confess that I'm procrastinating in the video. Okay, so see you next time.
Bye. Thank you.
Thank you. Have a nice
Thank
day.
you. Bye.
Thank you. Bye.
Bye.
Bye.